Well, first of all, I would like to thank the Institute and the organizer of this nice semester for the honor and pleasure to be invited, and even more to be given this quite strong distinction to be a Rothschild fellow. Myself, I know the name of Rothschild since my childhood, but just as a worldwide millionaire. And it turns out that maybe, okay, it is compatible, but there is another thing, in particular this fellowship, so I feel myself a bit related to name of Rothschild. And of course, thank you very much, Ilya, for a nice introduction. You have to, can I add just a bit of information? Because Sinai told you something about me, but he told me something about you also. And not that time that you mentioned, but a bit later, he asked me to be a member of the jury of your PhD. Therefore, since that time, we are quite close. And the subject here, it is, you are right that it is quite broad field and a bit pretentious title, but I am going to start from narrowing this quite strongly. So it is mostly, okay, for the beginning. Oh, excuse me. Now, the outline of my talk. First, I'll discuss certain general things. Then, this is already the strong narrowing. I'll speak on elementary excitation in disordered solids or quasi-particles, if you want. And it will be mostly in the context of the Schrödinger operator's random potential. Then there will be okay, according to the outline, the second chapter will be typical spectra. These are mostly random matrices, and then several concluding speculative remarks. Well, what are disordered systems, first of all? Okay, just it is not, of course, by no means it's not exhaustive list. Just several items. They are listed here in the order increasing, so to say, randomness. First, these are incommensurate media, and the typical example is a quasi-crystal, but it could be the media after there are certain magnetic transitions that produce the incommensurate structure for spins. Then there will be, so to say, chaotic media, a typical example, turbulent. Then amorphous substances, for example, metallic glasses. And then there is one more thing, which is not neither of these three previous ones. There are many things and new that in many physics fields people would like to say something about, so to say, generic case. And this is why I mentioned here. And as I said, I would like to discuss a bit of physics. That means that the mechanical, electric, and magnetic properties of this media, but at least all the time trying to pass to and fro physics, mathematical physics, maybe a bit of mathematics. Yes, and but from the very beginning, I would like to say that, as Ilya pointed out, the disordered field is a very big field, even not without well-defined boundaries. Therefore, it is just hold the word if you want. And there are many things, just to mention several. There is percolation. There are random walks in random media. There is a statistical mechanics of disordered system. That means phase transitions, where there is a fascinating things. For example, spin glasses, which have a lot of links with various fields. And of course, if we have statistical physics is phase transition, that means that it is interacting system. These are interacting system with not weak interaction to produce the phase transition. But there is another example of extended, so to say, condensed matter, where you have 10 to 23 particles. These are not a piece of just magnet for phase transition, but a piece of metal where electrons, they are doing transport. And transport, this is already quite close to us because, well, we are also, okay, I am going also to speak a lot about transport, but the difference, and this is a narrowing process that was mentioned already several times. The difference that what I am going to discuss, these are things in one body approximation in the terms, in physical terms, and I will not discuss at all just emerging subject of, so to say, many body localization, because it's completely, okay, there are many reasons. First of all, there is no time. So let me continue. Now, well, what is a notion? I am not speaking about definitions, too complex, just notion. What kind of things we have in mind, at least myself in this talk, saying disordered media. Okay, just let's recall what is ordered media. We have translation invariance. Either continuous or discrete, that means periodic, or just homogeneous media, yes? And disordered media, on the first glance, it is just a negation of ordered. But in fact, it is much less, because if you just negate, that means everything except translation invariant case, which is too big, the subject. Therefore, in fact, we consider the system at which there is a lot of structure. And in particular, what we have in mind, not, okay, what people have in mind saying disordered media, there are at least two properties. They are weak, but they are quite serious in many cases. So we forget about translation invariant case, but not completely, because now we assume that not the events are translation invariant, but probabilities are translation invariant. Therefore, if we have two events, one in the domain A of subdomain of your microscopic sample, and another in the domain shifted by a little a vector, then before we said that everything is here is like is here. Now we are saying that the probability of things that happens here, they are the same as probability of things that happens here. It is quite natural thing because, okay, but it is not sufficient. We have to, of course, assume that, so there is a certain randomness, there is a probability, and we have to assume on the top of just translation invariance in the mean, we have to assume that there is certain decay of correlations. That means that if you take a little a big, then the probability of the joint event should factorize to the probabilities of two events, and because of first property, it will be just PA times PB. Yes, and of course, this is just a bit vague from the point of view of any mathematician, the error, because there in probability and ergodic systems there is a whole hierarchy of this factorization. Simplest one is called ergodicity, next is mixing, then strong mixing, there is regularity, there is undeterminicity, etc., etc. But anyway, we have to assume two things together. One of them is translation invariance, and second, certain decay of correlation, which could be, by the way, quite weak if it is about ergodicity, and it is the case in commensurate system when we have just weakest form and nothing more, and it makes the system a bit special. Many people in this audience, they know that to say something and to find something, to obtain certain result on spectra of incommensurate system, randomness, does play big role. There are other methods, there is special technique, but in many cases, just this point of view is also, of course, very useful. Well, and what we have from that, we have quite general property that if we have an observable that corresponds to the system at big volume V, then this is just, we have a certain realization of our randomness, say distribution of configuration of impurities in your your microscopic sample of metal, and you study, for example, the free energy, conductivity, which are extensive quantity. That means that this observable is, roughly speaking, proportional to the volume, at least when volume is large. And it is reasonable to introduce and to study this quantity per unit volume. And there is this property which is called self-averaging. It was implicit in many things, early things in disordered system. It was first explicitly formulated by Lifshitz. Myself, I learned it from him. And there is a self-averaging property. That means that despite that these things for finite volume is random, at the limit it is not random. And that means you have as probability 1 the convergence of this quantity to the limit of the expectation. And this is quite convenient because first of all, it reflects certain just empirical facts, because we know that the conductivity of a piece of metal with impurities doesn't depend on the configuration of impurities. It depends on the concentration of impurities. A concentration is a parameter of the probability distribution. Therefore, this reflects, or for example, free energy of disordered system has the same property. So we have this property, and it follows immediately from the two properties, from the translation invariance in mean and the decay of correlation, because you repeat a standard argument to prove the thermodynamic limit. You just divide your big volume to subvolumes are still big, but not so big. You do the little corridors. They are small not to contribute to this arithmetic mean, and they are big to decouple correlations. And then you get standard argument from the law of large numbers. If it is independent, okay, if your randomness is strongly uncorrelated, weakly correlated, or you just use ergodic theorem if the correlation is strong enough. But nevertheless, in any case, you get an analog of law of large numbers or ergodic theorem that allows you to prove this result, which is quite general. It's, by the way, the same in systems with interaction. This is why I call the first chapter generalities. But there are exceptions. This just let me to mention. If your volume is not big enough, because on the previous slide you have seen just V to infinity, that means that volume is indeed big. If volume is not too big, for example, about 1 micron, then it was observed in many experiments that these are small metallic particles. There are fluctuations of conductivity, and it was found eventually that there are fluctuations. Therefore, there is no self-averaging because the system is not big enough. The remarkable thing was that there are fluctuations, but they are universal. Otherwise, it would be quite hard to say something, because you have a strong dependence on realizations. You have nothing more or less, well defined. And this is the field was quite flourishing in the end of 70s, beginning of 80s. There were several groups doing this. In particular, in this audience, we have Dima Khmelnytsky, who contributed a lot in this field. Now, let me pass to the second part. It is elementary excitation. So I repeat, what is it? So formally, it is just ideal gases of electrons, phonons, whatever. And I repeat, this is a called quasi-particle description of condensed matter. There are many subtle things in the criteria how to and when to apply, but I will skip that, just assuming that we are able to describe strongly interacting system in certain intervals of energy as a gas of elementary free particles. And then the problem reduces to the problem to study one body operator. That means the operator of finite number of variables. Typically, and even archetype case, this is Schrödinger operator or Schrödinger equation with random potential, discrete or continuous. And these are three typical examples of random potentials, which reflects these classifications that I gave before. So there is the first potential. You have just a lattice of xi's which are not random, and at each lattice you have a random potential, random bump, which models somehow an impurity, or better to say, These are just so-called substitution alloy. Typical example, for example, the copper gold, which is which could have at each side of the lattice. The lattices of copper and gold, they are almost the same. And if you add to, say, a copper a bit of gold, they are sitting at the same sides with probability equal to the concentration. So we have so-called alloy type random potential. All size are IIDs, for example, excuse me. So you have a sufficient amount of randomness. This is the first example, typical. Second, you have just chaotically distributed points. These are Poisson points. This is a kind of model, simplest, a toy model of amorphous medium. And the third example, these are just, you see, simplest quasi-periodic function, which models is simplest model of, say, quasi-crystal. If alpha is irrational, of course. If alpha is irrational, you have a periodic case. And you are back to ordered case. Well, and this eventually, okay, to describe all these things in more or less general frameworks, it turns out to be useful to introduce the notion of ergodic operator, which is you start from standard triple of probability theory, probability space, sigma algebra, and the probability measure, and you add a group of measure preserving transformation, and these things is known. Sometimes it's called abstract ergodic system, and then you consider the operator either matrix or integral operator, differential integral operator, acting either here or here, and you assume the property of its matrix or its kernel that a shift on the realization could be translated to the shift of the arguments. Yeah. If you assume for the moment that your omega is trivial, just consisting of one point, then you are back to Toeplitz operator, which correspond to the translation invariant media. Yes, okay, but it is just for a bit of abstract things, because I'll mostly discuss just Schrödinger operator. And now, most fascinating thing so far in this field was, of course, Anderson localization, which was introduced by Paul Anderson in 58. We had already, how much? Almost 5 years ago, in 2008, we had here a semester dedicated to 50 years of the first paper, 50th anniversary of the first paper by Anderson on the localization. And let me explain just a few words what is localization from the very naive point of view. Let's recall the elementary problem, so to say, qualitative problem. I'm not going to solve it completely. You know, just corresponding ideology. You have two wells. The distance between wells is A. Assume first A is infinity. Then you have two separated wells. Each has just one single level and one single corresponding eigenfunction. Then you assume that A is finite. At the beginning, maybe big enough. And then you introduce two parameters, so to say, that characterize the unperturbed problem, two infinity remote wells. So this is the energy mismatch, I would say, and it's called overlap integral. And there are two cases. Okay, first of all, okay, this certain calculation shows that if A is big enough, then the new this is unperturbed things, A to infinity. Now A is finite but big enough. Then new thing, now you have a unique operator instead of direct sum of two, and you have two eigenfunctions already when A is finite, denoting their eigenvalues capital E and psi. You have two cases. So capital E's eigenvalues are close, exponentially close to the unperturbed ones. So it is simple. But as for eigenfunction, it's much less simple, because it depends now on the relation between these two parameters, the energy mismatch, level mismatch, and the overlap integral. If you have this situation, if levels of an unperturbed system are far enough one from another, then the perturbed eigenfunctions, they are with exponential precision the previous ones, unperturbed ones. So the particle is still sitting in its own well. But if you have an opposite asymptotic regime, in particular form, if these two wells are the same, just the same shifted to the same well shifted by A, then you have completely different situation, because now eigenfunctions are completely collectivized. Yes, this is first, we say that there is no resonance tunneling, and here you have resonance tunneling, and it corresponds, it gives rise to two mechanisms of localization. First, more or less intuitively clear, these are just, if disorder is big enough, you just, localization is just a trapping of your particle, of your electron in a particular well. But if energy is big enough, then there is another mechanism which corresponds to just small deviation from resonance tunneling, and it's called enhanced backscattering. I'll be back a bit later on the same. Now, so it is two wells, it's elementary thing. Now, of course, the business is what to do with many wells, with macroscopic number of wells. And you have to find two situations by using your parameters of your problem when you have one of the two. Either you have macroscopic tunneling. So you have a resonance tunneling in the macroscopic number of wells. A typical example, just periodic wells. This is a crystal. And then, of course, there is no localization. All the new eigenfunctions that you get just bringing atoms from the infinity to a finite distance, you have a periodic solid, you have bands, and etc., etc. And if, on the other hand, situation is that the tunneling is still between just few wells, then you have localization. And long time ago, just lecturing on that subject, I used to say students that, you know, localization just the result of activity of quite negligible careless person. Just putting wells, absolutely no care about their order. So it is simple story. While to get a resonance tunneling in 10 to the 23 places, you have to be either very, very meticulous person or just a god, because there is no way. So you have to provide tunneling in the enormous amount of wells. This is correct, but nevertheless it turns out that to prove localization is harder than to prove to study the periodic case. So we have localization just because, despite that we have now macroscopic number of wells instead of two, the situation still is similar, at least correspond if we are about the first situation. This one, no resonance tunneling. Oh, it's very bad color. It is written no resonance tunneling. Well, so we have localized states that, despite that we have wells everywhere, your quantum particles sits in a certain well, depending on energy, etc., etc. Yeah. While in the case when you have periodic situation, the quantum particle is more or less uniformly distributed over the whole crystal, and we have this situation. Now there is a third situation which corresponds the classification of abstract spectral series. There are three types of spectrum. There is point spectrum, there is absolutely continuous spectrum, there is singular spectrum. So this third kind of spectrum also appears in disordered system, but in not too strong, not too much disordered. That means mostly in the quasi-periodic cases. Well, we have this situation, and as I said before, localization was first formulated in explicit form by Anderson, and there were Ilya Lifshitz and Neville Mott, who was here for many years in Cavendish laboratories, that contributed a lot to the things, just the same, more or less at the same time. Yes, and the last thing, that what is a spectrum, typical spectrum of the, say, Schrödinger operator with random potential. Now I am about just a band or a discrete case when spectrum is finite. So the near band edges, we have always, for any strength of disorder, we have certain amount of localized states. If the disorder is not big enough, the localized states occupy just a part of the whole spectrum, and the boundary between between localized and non-localized spectrum is called mobility edge after mod. By the way, the very existence of these things is still not proven mathematically. We know everybody believes, but still it is not proven that that could be an overlap, for example, between these two spectra, or their points, etc. But nevertheless, there is a lot of physical and numerical results now showing that this picture is correct. That if we increase the disorder, these mobility edges will move one to another, and eventually they merge. In that case, we get the situation when all the wave function, all the states will be localized, and there will be no transport. The electron will not go through the crystal, and this is in complete correspondence to the title, this paper by Anderson, which is whose type is absence of diffusion in disordered system. Diffusion means electrons, yes? Well, and this is new notion of the insulator, because standard classical notion, which as far as I know was worked out here in Cambridge. Dima, am I right? Wilson was here? Yeah. So according to which what is a insulator? You have a just periodic system, but you have two bands, conductance in the valence and conductive bands, and there is a gap between them. And electrons fill the valence band, and we have it can't jump over the gap if the field is not strong enough. So we have an insulator. But if the bands overlap, then you have conductor. But here we have another notion, because if we have a portion of extended states, then of course we have a conductivity. But if the extended state disappear when mobility edges, these are even a name suggests what is going on. And if they merge, then there is no transport, there is no propagation of particles via your sample, and we have a insulator but completely different mechanism of the insulated states. Well, what about just a bit of math, because according to the prescription there should be lecture of broad subject, but for the mathematical audience, therefore I have to say something about mathematics. Just few results. There is a lot. I am not able to mention all the things, and I just apologize in advance of all incompleteness of my references. So in D1 we have now, it was first suggested by Mott that in one-dimensional case, and of course if your potential is random enough, then you'll have complete localization. I mean random enough, the correlation decays, but the amplitude of potential could be any, just very small, and nevertheless you have already localization. For a dimension bigger than 1, we have at the moment we have the regime of strong localization, that if potential is big enough, then you have a localized states for the part of the spectrum, and this is precisely what is described on that slide, previous slide. And it was again the effort of, even so far, the interesting work on that topic, but the two crucial papers were Fröhlich and Spencer, and then Eisman-Molchanov. There were two different approaches to the problem of strong disorder. Mostly in Eisman-Molchanov there is a small issue concerning the weak disorder, but nevertheless it is basically strong disorder which we have now. And of course in doing that we gained a lot of information and new understanding about the structure of spectrum of typical operator with a bounded potential, because before that what did we have? We have basically three cases. We have a growing potential at infinity. This is more or less trivial thing. Resolvent is a compact operator, spectrum is discrete and finished. It was done before war by Röhlich and many people. Yeah. Another case, decaying potential, this scattering theory, fascinating field. Potential is absent at infinity. You have scattering. There is a lot of interesting mathematics around, and it's basically done. And the third type, neither growing nor decaying, The only case roughly, but not roughly, but precisely, was a periodic case. And we had the absolutely continuous spectrum consisting of bands, etc. Now we understand that a random potential which doesn't grow because of translation invariance in the mean is systematic. It could oscillate, but it doesn't grow. And nevertheless, we see that for random case, or more general for random and almost periodic case, we have much more. We have, according to the list that I gave several slides before, we have just all the types of the spectrums that are prescribed by the abstract spectral theory: pure point, absolutely continuous, and the singular spectra. So it is much more rich collection of cases, much more rich collection of methods and results. It came with with the notion of ergodic operators and the random, almost periodic, etc. So it is if we are just strictly spectral theorists. But of course, there is a lot of things around, both when you study and both just if you're thinking about more about mathematical physics around, not to mention theoretical physics. Yes? So let me mention several, just a small collections of results. Well, just a collection. First of all, density of states. The basic thing, you take big volume, you compute how many eigenvalues you have in an interval, and then you do macroscopic limit, volume to infinity, you get a function which is just limiting, normalized counting function. Counting function is quite respectable object of spectral theory, suffice to mention enormous amount of papers on the Weyl asymptotics that concern the high energy eigenvalue distribution or the Schrödinger operator in the compact domain. Yeah, it's a bit different quantity, but basically the same. And if we about the ordered system, just a constant potential or periodic potential, at the edge of the band you have power law 0. Okay, the density of states tends to 0 in dimension bigger than 1, then 3, then 2, better to say. Okay, it has either, if we about all the dimensions d1, 2, 3, etc., we have either power law 0 or power law singularity, no more. It turns out that if we are in the disordered case, at the edge of the band, this is the edge of the band, we have much stronger 0 than just power law. For example, in three-dimensional case, density of states tends to 0 as this difference to the power 1/2. And here we have 3/2, but in exponent. It's called Lifshitz-Thales, and there are many explanations, etc. Let me just mention that myself, I also used to think that it is a kind of large deviation theory, but in a spectral context, if you want. But it requires a lot of things, even being the simplest possible quantities. Then there is very nice result which came, not immediately after the first papers. This is about so-called dynamical localization. It's quite natural thing. If you take just spectral projection on the interval delta of spectra and just its kernel, and it turns out that expectation of this spectral projection decays exponentially, and the rate of decay is, roughly speaking, is just a localization radius. It is the scale on which your eigenfunctions, localized exponentially. Yeah. Now I am listing the results in the order of more complexity, and the further we go, the less we know. Yes. And now there is an important result which is, so far it was just spectral theory. Now there is a bit of physics. If you have our ideal gas of electron in random field, which corresponds to in quantum description to the Schrödinger equation with random potential, then the conductivity of this gas is 0. It is just, if you want, it is again, this is in fact initial result by Anderson, which in fact assumes that it is the case, and even presented certain arguments in his famous paper. I read once an opinion by Mott, who got the Nobel Prize together with Anderson, that this is a famous paper that everybody cites, nobody understands. I mean the proof. But nevertheless, result is correct. It was proven at least partly now. And there is one more field in which localization was quite useful is the integer quantum Hall effect. And let me mention a certain application to a new field, which is now just quite active. There are hundreds of papers on various topics. This is called entanglement. Okay, this is quantum informatics. And there is a quantity which plays important role called entanglement entropy. I have no time to discuss physical meaning, but from the point of view of mathematics, you have a simple thing. You take a projection, spectral projection of your random Schrodinger operator on a given interval delta, then you make a restriction of this projection on a finite volume, and you compute the trace of this finite, okay, the compact operator, or even finite dimensional in discrete case, the trace of h of p subindex lambda. H is just a standard binary entropy of, okay, binary entropy if you have information theory just. So, and it turns out, so there is a big problem. The problem is much more general. It is about, in fact, interacting system. And there is a discovery made, by the way, in black holes, in astrophysics and high energy physics, that this entropy corresponding to a given volume, in general case definition is much more complex. But it behaves like that. If the spectrum, your operator, has a gap, in translation invariant case, it was, okay, there were many people who made this conjecture. There is not place even to listen to them, but basically it was Bekenstein, I believe, and Wilczek and co-authors. Yes? Then if there is a gap in your system, then translation invariant case, the entropy behaves like the size of your box, but in the power dimension -1. It is a big surprise, because in statistical physics, the entropy is proportional to the volume. It is just extensive quantity. And here we see that it is just proportional to the surface, this is why it's called area law. But if there is no gap, then you have an extra log term here. So it grows faster. And there are certain proofs on the level between mathematical physics and theoretical physics of this result. There is Michael Hastings who made a lot. But if you just, it turns out that there is a toy model for this field. You just consider disordered fermions. They do not interact. And you are inside, you take your interval inside the spectrum. Therefore, there is no gap. And nevertheless, it could be proven. Yeah, excuse me, I forgot to say that the conjecture was due to the many people, but the proof in one-dimensional case, this result was proven, this is especially hard, was proven by Harold Widem in the 80s, and the many-dimensional result was proven Sasha Sobolev, who is here in London, just a year or two ago. Because it's related to the Sega theorem, not smooth symbol, turns out that mathematically it's quite hard thing. But nevertheless, you have two options, one of the two, depending on whether there is a gap or no. It turns out that if you are in disordered case, then you have all those, I repeat, all those. Either there is a gap or there is no gap, you have all those area law. There is no this log term, and there are several proofs. Okay, there is a proof. It is not completely rigorous so far. Okay, it is rigorous, but just a few months ago. But in this paper, it is not rigorous. We just found two bounds from below and above, showing that the expectation of your entropy behaves like this case. So there is no, this behavior called violation of area law. Yes, and I learned that Unterstolz got similar results even for interaction systems. And okay, this is just in this lecture I just mentioned as a possible application, and to prove this, in fact, you need basically only to know just this thing. You have to know that there is dynamical localization. So dynamical localization is proven in one-dimensional case for all energies, in multi-dimensional case for low energies, and in the almost periodic case also, Lana, for all energies. Yeah, but this order is strong enough. Yes, I believe. Yeah, so if you have localization, you have this. So it is somehow, it goes together, yeah? Well, just recently we were able to prove with Masha Sherbina that it's interesting story that if you have, this quantity is random, so this result is about expectation. But it turns out that if you ask yourself, what is going on with realizations? And it turns out that in one-dimensional case, the entropy is not self-averaging, it fluctuates, it depends on realizations, and it is quite, in a way, annoying story. But if the dimension is bigger than 1, it is self-averaging. In my more or less big experience with disordered system, it is the first case that the effect of self-averaging depends on dimensionality. But nevertheless, we have a new thing, a new application of localization theory. Now, let me pass to a bit more harder things. There is a graphene, which is interesting thing. This is just monoatomic layers of pure carbon, yeah. And here, we, instead of Schrödinger, we had to study Dirac operator. And in one-dimensional case, it's simple, because it turns out that if you write this operator, there is no localization at all. Because it is, in physics, it's known as the Klein paradox. I have no time to discuss. But if you add this potential, which is called chiral effect, then you have localization, you have a lot of things, still not too much studied by mathematical physicists and spectral theorists. Well, next thing, more hard, it's about conductivity. For, you see, the localization was introduced by Anderson to prove, to show that there is no conductivity in random media, and the spectral theory, despite all its successes, still is not able, okay, it is able to prove the conductivity is 0 for DC, for direct current. But there is a fascinating formula, for me at least, which was written by Neville Mott, that if you take a not zero frequency, so you have a electric field of frequency nu, and you are interested to know what is a low frequency behavior, and there is a formula, asymptotic nu square, and the log term. Every time when you have a log in certain asymptotic, it's interesting and hard to prove. This formula is still a question, there are bounds, okay, I have no time. There are interesting effects here, excuse me, yes. And there is a basic question, there is a ultimate goal of our field is to prove that there are still delocalized states. I mean, okay, there are many things around. There is a very nice development again of 70s and 80s in theoretical physics, which called weak localization, where people, in particular again, Dima Khmelnytsky, Louis here, people were able to find what is going on if you study just a very weak disorder, small concentration of impurities. There are certain effects that is here, but still the problem of to prove that the delocalized states, as many in this room know, still an open problem. And this is just a particular case. This is one body situation, a particular case of more general question about transfer phenomena. But in my opinion, okay, I am a bit puzzled what is going there, because from the point of view spectral theory, because I do not see so far which spectral theory is quite interesting, and I believe interesting, and there is a lot of perspective in this question. But spectral theory, so far I don't understand how it could be built here, because we have to deal with the operators with 10 to the power to the 23 number of variables, and how to deal with this operator. It's not clear question. Let me pass, I'm a bit late already, to the second topic, which is as random matrices. This is a field which is mostly starting from 50s, more or less the same time, by the way, a bit earlier than Anderson. The founding father of this field is Eugen Wigner, and his first paper is 52, and the first paper by Anders 58, both in Princeton. Yeah, and so what is it about? It is much simpler mathematical. It's in just a matrix. You have a n by n matrix. In fact, in random matrix theory, we used to say we have a matrix. In fact, we have a sequence of matrices for each n, and we are going to take n big. So there is a sequence. For any n, you have a matrix. And now there are two basic examples of matrices studied mostly so far. First matrix, you just take x, y, j. These are variables. I forgot to write that they are symmetric. Excuse me. What is going on? Stop. It's a mistake. Excuse me. Some mixture in the slide. Okay, let me write. It's some mistake. So we have two types. First, we have a matrix. Forget for the moment that there is this factor. You have just jk from 1 to n, and x, jk are symmetric. And modulo this condition, because I would like to study symmetric matrices corresponding of adjoint finite dimensional operators. Yeah, and the most important thing is that modulo these conditions are independent. The entries are independent. And what is an IIDs? So in this case, all the entries of your matrix, they have the same order of magnitude. It's completely different from the Schrödinger operator, where if you take a random discrete analog, you have principal diagonal in two adjacent diagonals, not zero, all others are zero. And here, all the entries are of the same order of magnitude, and it's called GUE. Okay, excuse me, this is just PowerPoint. You're never sure that everything will be there. Yeah, so it is a matrix with zero mean, and you see this IID, and just you have to, since they are Gaussian, suffice to give the expectation at the second moment. And okay, this matrix is. This is your second. Huh? I think this is your second. Yeah, but there is a mixture because excuse me, because this is about the first case, but my God, I don't know. It's not me who changed the order. Okay, yeah, you are right. This is my second case. Excuse me, please. So we have this situation which has a special name, Gaussian orthogonal ensemble, and but in fact, historically first. Now I understand because it's historically first. The historically first random matrix appeared in statistics in the 30s. Yeah, and it is it's called sample covariance matrix of your. If you have there is clear statistical meaning of these things. So you have in both cases you have how to say Gaussian random variables, but here your matrix just Gaussian, entries are just Gaussian. Here they are bilinear, and you ask a much simpler question at the moment. You ask just about what are eigenvalues of this matrix, at least asymptotically for large n. Yeah, we are looking for large n properties of eigenvalues. We introduce the standard thing in spectral theory, just the eigenvalue counting measure, just giving you a number of eigenvalues in a given interval among the all. Yes, the physicists call it integrated density of states. And then there is a bit more general object called linear statistics. You write in that form where phi is more or less arbitrary function called test function. And this setting comes from statistics. And you're interested to know what is going on with this n when capital N when little n is big. Okay, we have. Let me just give a bit advertisement. It seems not too deep subject, not too complex, and not too rich. And nevertheless, so far, there are fields listed here in which random matrices are useful. And the natural question, why? Okay, there are many answers, of course, on that question. Let me mention. Okay, this is a bit. This I skip. Okay. I'll just on that slide there is something else, but I have no time. Just read these two things. Okay. First of all, when you make the expectation with respect to random matrix, you integrate over n square independent random variables. N tends to infinity, so you have multiple integrals. And just recall in statistical mechanics, we understand that we could describe a lot studying the multidimensional integrals in the limit of infinite dimension. And second, the just attracting point, because it was used in many fields among the listed myself, is just because somehow people were interested in many fields what is going with typical operators in typical spectra. And somehow, in certain sense, random matrices, they give an answer on that. Well, and just a short list of results. There are 3 groups of results in random matrix theory. First, all of them, they could be formulated in terms of this term of this linear statistics. So there's a choice of this function phi. If you just take function phi which doesn't depend on n, just a function, okay, better it is if it is just C1, a bit complex if it is not C1. Nevertheless, you take this function which is independent on n, and you are able to prove an analog of law of large numbers, which reminds us the existence of the density of states in random Schrödinger in the case when you have a ergodic situation. So the limit exists with probability 1 is not random. So it's self-emergent property of the density of states. Yeah. And even in many cases, you can find explicitly the limiting density of states, the density of this limiting measure. There are 2 basic cases. First was found by Wigner. This is for Gaussian orthogonal ensemble. It's called Wigner ensemble, in fact. Yes. And in another case, it was Marchenko and myself. We found for sample covariance matrices. But there is a lot now. And what are applications? There are 2 basic applications. This is, okay, let me mention just one. Okay, there are fluctuations of, you can describe the capacity of channels, telecommunication channels with many users. For example, the provider of certain, okay, Orange or, I don't know, Kyivstar in Ukraine. There are many providers that provide you the mobile, just a cell phone service. There are many users, and you can describe a certain processes in these telecommunications by using random matrices. Well, it is just for fun. You see, it is a Wigner semicircular distribution. You see, it converges quite fast. The first curve is just a one-dimensional matrix, just random variable Gaussian. Here you have 5-dimensional matrix with this, and if you have the limit, you have quite already similar things. So it is quite fast conversion, and it is important in many things. Yeah. Now there is intermediate regime when you choose your test function just in this form. What does it mean? That you choose a certain point in the spectrum, lambda naught, and then a small neighborhood of that point. In this choice, the neighborhood is of the order 1 over n to the power alpha, but alpha bigger than 1, sometimes equal, and less than 1, bigger than 0 and less than 1. Yeah, and you can prove, for example, again, of course, it's extremely simple to prove that there is a density of states, but it turns out that if you compute the variance of your linear statistics, what is the density of states? Just the arithmetic mean. So your probability experience says you that if you have a law of large numbers, you have to have convergence with probability 1. Next term should have Gaussian oscillation. There should be central limit theorem. Yeah, but it turns out, yes, there is a central limit theorem, not always, but if yes, the variance doesn't grow with n. We know that in the case of independent random variables, the variance grows linearly with the number of terms. Here it is just bounded. It has a finite limit. So the correlations between eigenvalues are much more strong. And this is if function phi is smooth. If it is just not smooth, just a step function, an indicator, then you have a log, which, by the way, strongly related to the logs that I mentioned in entanglement entropy. There are connections. So we have, and again, there is a very nice application. I mentioned before mesoscopics, in which there are universal fluctuations of the conductance. It turns out that one of the explanations, not unique, but one of them, is just because this property. The variance of linear statistics of random matrix theory is n independent for large n. Well, And the last thing that is important, it is so-called local regime, when you choose the size of your neighbor to the order 1 over n. And here there is a famous conjecture. I believe it was Dyson who first formulated it explicitly. There were certain feelings before in 72 that whatever random matrix you have, if there is enough of independence between entries, say they're independent or weakly dependent, then in that regime, the quantity written here, the probability that a small interval is empty, there is no eigenvalues, yeah? You make a windows of the size 1 over n. Forget about this normalization, just to have a nice answer. In fact, you take a lambda naught you choose, and then you just take a window of the size 1 over n, the n is the size of matrix. And the conjecture is that this quantity at the limit, when you take n to infinity, will have an universal form written here. And at least part of this audience already have heard about that in the talk of Igor Krasovsky, who studied certain asymptotics of this Verdwood determinant of the sign kernel. Yeah, and this is proven more or less in last 15-80 years. Okay, there are several groups of people proving that, but just let me mention an important application of this thing. So if you know this gap probability, you take just two derivatives with respect to this scaled length of the interval, and you get an important quantity. I'm finishing in 5 minutes. Yeah, important quantity, just the probability distribution of spacing between nearest eigenvalues. And okay, this is universal. It does depend on the matrix in question to a large extent. It depends, in fact, on the one thing, whether your matrix is Hermitian or real symmetric. And this is by the index beta, which is for the real symmetric 1, and for Hermitian is 2. And you see for small s, you have s to the power beta. That means that eigenvalues, they are repulsing one another. They do not want to live close enough to one another, because the probability to have two eigenvalues on the little distance in the scale 1 over n vanishing. And this property of repulsion turns out is important to a number of things. Okay, the subject is quite old. It dates back to the famous in quantum mechanics paper by von Neumann and Wigner. But let me just show you several pictures showing where it appears. Yeah. So this is just this picture is not about Hermitian matrix, but about unitary or orthogonal. It turns out that with respect to local properties, when you are dealing with a little neighborhood of given lambda, this is the same. Hermitian and unitary, they behave locally the same, and the real symmetric orthogonal also. So this is just numerical results. So these are just, you take random points, independent random points on the circle. And you see there are clusters. It is far from being uniform. While if you take random unitary matrix, what does it mean? You take the unitary group UN of big, n is big, and you assume that just you view group as a probability space, R measure as a probability measure, and your matrix U now is random, yeah? And you compute its spectrum, you make a numerics, and these are results. You see, there is to large extent, this is uniform distribution. So there is repulsion. So there is a small probability to be close enough is small, and also probability to be far enough is also small, even much more. It is exponentially small. You see, probability to have large spacing is exponentially small. So eigenvalues, roughly speaking, physicists used to say sometimes that eigenvalues of random matrix, they are like sides of a crystal, because the distance between them neither big nor small somehow, okay, between of the order 1 over n, yeah? And here you see the nice picture of this PS. This is just probability distribution of spacing for, you see, Poisson, standard exponent. We have clustering here. This is the histogram. You see, what is it? This curve, which is just Gaussian orthogonal ensemble, which I mentioned before. And now, this is just, this is the nuclei of erbium. And you have 108 spacing. And this is a histogram, you see, it repeats more or less GUE curve. This is why Wigner introduced matrices. He would like just explain this experimental, to explain this experimental fact. Yeah? And now it is more or less explained. But it turns out there are much more sequences when we have the similar distribution. In some cases we are able to prove that it is correct. In some cases we have just numerics and good conjectures. Yeah? So you see here again Poisson, and there is a clustering. Yeah? This is prime numbers. There is still clustering. Now we go into the same nuclei of erbium. There is less clustering, already a kind of more or less uniform. Now you go to Sinai billiard. Sinai billiard, it's an archetype case of chaotic system. Chaotic system a bit similar to the random system. You can describe it in there are certain arguments, physics arguments, that allows you to describe this case, this system by using random matrices. And you see that it is justified because distribution is already to a large extent uniform. Now you go, I believe that everybody here heard something about that zeros of zeta function, they are also described by this distribution, which comes from random series. It is quite already uniform, and here just uniform distribution. And let me finish to make several, just in fact, two speculations. The first is not a speculation, but widely accepted conjecture in spectral theory. Just let's compare. What do we know about the eigenvalue spacings, distance between nearest eigenvalues? So just in the first part, I listed all the cases when you have corresponding to the previous picture, where you have this so-called Wigner-Dyson distribution, which is for random matrices. You have a lot of different fields, and the last one, which concerns us, is it turns out that it is a conjecture that if we are in absolutely continuous spectrum for infinite crystal, for infinite system, for big enough but finite system, we have to have Wigner-Dyson distribution. This is a conjecture. There are certain, partial results confirming the conjecture, but still no proof. On the other hand, this Poisson distribution is another limiting case when levels are not correlated. Okay, this is more or less proven that it is the case in integrable systems. And the second case, these are eigenvalues in the localization regime. It was rigorously proved first by Molchanov for the one-dimensional case, just continue our joint work with Ilya. And then it was proven by Minami for arbitrary dimension, just basing on this strong localization approach. Yeah. So, and now there are many discussions that, well, we are not able to prove that there is absolutely continuous spectrum. But at least let's try to prove that instead of absolutely continuous spectrum, we have this Wigner-Dyson distribution for high energies, or in the middle of the band. It is still not proven, but okay, there are certain hopes. Yeah, and now let me finish just speculating a bit more. There is a folklore in both fields, random matrix theory and the random Schrödinger operator, that random matrices, they are somehow mean field approximation for the random Schrödinger. Okay, I am not sure that all the mathematicians here, they know what is a mean field. Therefore, let me say several words. We have a standard classical, say, or quantum, doesn't matter. You have a system of particles that interacts, not ideal gas like before, interacts via pair interaction, but we choose the interaction in special form. We just make interaction like that. So we have a function phi, and whose support is 1, and now our interaction is written like that. That means that the radius of interaction just r. R is finite thing, yeah? So all the particles that are in the inside of the sphere of the radius r in a given particles interact, and outside no. So, but it is per interaction, and it was proven. Okay, the folklore was known since end of 19th century, Curie-Weiss, van der Waals, etc. But if you take R big enough, then it was proven in the 70s, first by Van Kampen and then Leibovitz and Penrose made the rigorous proof that when you compute the free energy for fixed R, macroscopic limit, infinite crystal, yeah, and then after that you make R going to infinity, you'll get van der Waals theory. So it is a kind of justification showing that van der Waals theory or Curie-Weiss, which is mean field, you obtain from short range case just making radius of interaction bigger and bigger. Let me show a bit of analog in the random matrix theory. Now what I do, I would like to consider a random operator, infinite random matrix, yes, because you see here is ZD, which is written in that form. You have a similar function like I wrote before, yes, and here we have W, X, Y. This is just random Gaussian independent random variable, infinite matrix. But you cut it because the support of function phi is 1. So you take infinite matrix W, X, Y, infinite in all dimensions, and then you cut a band of the width R in around the central principal diagonal. Sometimes it's called band operator or band matrix. And you fix R and you compute the density of states. Okay, it exists. Unfortunately, you can't find it explicitly, but it exists with probability 1. This is a result of ergodic operators theory. But it turns out that if after this, just expanding your box to the infinity, and then after that means doing thermodynamic limit, and then sending R to infinity, you get, for the density of states, just Wigner law. So it is weak, but nevertheless positive result showing that is indeed random matrix theory is a kind of mean field approximation, and it makes a certain hope that by using not random Schrödinger operator when you have just nearest neighbors interaction, but just band matrices where band is big enough, maybe we would be able to prove that there are delocalized states. And the speculation is like that. Let's consider the eigenvalue density of states for finite R. The Lifshitz tails, you see, this density of states on the band edges is quite small, exponentially small. Now, but if R is big, it is written on that slide that you see, we have, let me remind you what is a semicircle law. It is just very simple. It is indeed a semicircle. You have, so you have here just square root of E minus, okay, E naught minus E. Here, this is E naught. Yeah? And there are no Lifshitz tails. And Lifshitz tails, everybody who worked in localization, we know that Lifshitz tails, these are simplest manifestation of localization, of strong localization. And there is no, since there is no Lifshitz tails, somehow one is inclined to believe that maybe just taking R big enough, we would somehow locate where the mobility H, and therefore if we are far enough from the edges of the semicircle law, somewhere here, maybe we could be able to prove the existence of delocalization. There are several groups of quite strong groups working on that subject. There are many results, but so far no the final result. Thank you very much.
Promote some non-trivial ideas concerning this EC and many other things, those who listened carefully. Anyway, we finish it here, and there is some informal reception there, waiting, I mean, something which is called.
Yeah, but maybe there are questions.
Waiting for us. Huh?
Maybe there are questions.
No. I was quite.
I'm not sure, but just for the case.
I was thinking about that, but it's not that I care about the time. I'm the last person to be worried about 10 minutes, being 10 minutes late. But usually, no, let's somehow break the tradition. Yes, questions, please. If there are. Usually in lectures of this sort, we don't ask too many questions. That's why I didn't bother about that.
I think Leonid said a lot of questions during this talk.
Yes.
So-
Well, that's what I'm trying to emphasize. That there were, in fact,
Hello.
many interesting
I
questions.
think the tradition is to have discussions during wine.
Well, maybe it's better.
Ironic.
Best option, yeah, best option. Just continue drinking wine.
Is it okay?
Yulia, go ahead. Yeah.
So, do you really think that when we have a semicircle law that we have a delocalization? Is it as simple as that?
Look, but I made a lot of stipulations. I said that it is an idea, maybe, but you have to work with the band matrices. It is the finite difference operator is very high order. Roughly speaking, what I am saying since it is hard to prove the localization response for discrete Schrödinger, multidimensional, yeah? Let's consider it is second order operator in the ZD. Let's consider the operator very high order, but finite. That maybe we will be able to find a portion somewhere in the middle of the band of the absolutely continuous spectrum. Okay, there are some partial results indicating that it is not a crazy idea, but we are far from definite proofs.
Maybe I will ask you more questions during the wine.
Okay, thank you.